All right, so this is going to be the NMSI rotational motion free response key. So this is going to be question 1. So let's see what it says here. So you get a little diagram of a hinge and a spring scale and a mass at the end of the bar. It gives us the length, it gives us the mass and mass of the bar. So let's see what it says. The horizontal uniform rod shown above has a length of 0.6 meters and a mass of 0.2 kilograms. The left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a cord that makes an angle of 30 degrees with the rod. A spring scale, no mass, measures the tension in the cord. A 0.5 kilogram block is also attached to the right end of the rod. A, on the diagram below, draw and label vectors to represent all the forces acting on the rod. Show each force vector originating at its application. All right, so let's see. Let's see what we got here. All right, so we got, let me draw the rod. This is the rod. So let's see. Obviously, the rod has some mass. It's going to happen right in the center of mass. So the rod's weight, that's the rod times gravity. There's that mass at the end. So that is going to have mass of the box times gravity equals weight of the box. So that's rod. All right, you got tension in the string applied this way. And then if you look, we got to even everything out. It's going to be, there's going to be, so that's tension. And this is going to be your hinge. It's going to apply force that way. That cancels out because if you break this down, it's going to be, so to compensate, you're going to have some going this way and then some going up to compensate for these two down here. So there's your 4 forces. Hinge, tension at the 30 degrees, weight of the rod in the center, and weight of the mass at the end of the rod. Okay. So let's go ahead and clear that. So that's this is going to be B. It says calculate the reading on the spring scale. So what we're going to do is we're going to take the rod to rotate at the hinge. So we're going to look at the torques acting on it. We know it's in equilibrium, right? So we know it has to be 0, and we're going to start observing it from the end. So what I'm going to have here, so if I have it at the end, I'll draw it again because it might make it easier to. So I'm going to have weight of the rod, I'm going to have weight of the block, and I'm going to have what's called tension. Okay, so I know summation of the torques must equal 0 because we're in rotational equilibrium. So when I go ahead and do this, let's add up the torques here. So we know that the rod, what's the length of the rod? 0.6. Well, let's just do it in variables for right now. So let's take into account the mass of the rod. So I got mass of the rod times G. And remember that torque is RF theta. And so that's the force is mg, force. The R is going to be half of the length. So L divided by 2. Okay? And that is going, that's going clockwise, right? Yeah, that's going clockwise. So let's go ahead and do this. And we'll get M of the block times G. I don't know why I made this capital. Let me erase this real quick. Sorry. That's the force. It's at a distance of L. And then the last one, the tension is going counterclockwise. We'll make that negative. It honestly doesn't matter. I actually think on my work I did it opposite. So remember, we want the force, and this is at 30 degrees. So when I plug in with this, I got my radius is going to be L, my force is going to be T, so it's LT sine 30. All that has to equal 0. Okay, so I can plug in. What's the mass of the bar? 2. So I got 2 times 9.8. Length of the rod, where does it say that? Oh, it's 0.6, so I got 0.3. It's half. Mass of the block is 2 kilograms times 9.8. Length of the rod is 0.6. Minus length of the rod is 0.6. Tension is what you're looking for. Sine of 30. 0. Solve for T. Basic algebra, you can get 29 units. All right, so that's B. C. So now it says, if the cord that supports the rod is cut near the end of the rod, calculate the angular acceleration of the rod block system about the hinge. The rotational inertia of the rod block system about the hinge is 0.42. So it gives us I. It says the rotational inertia 0.42. So now it's basically the same thing, except there's no tension in the string. So we're going to ignore that one. And we have to remember that summation of the tension is equal to moment of inertia times angular acceleration. To give us moment of inertia, we just got to summate, we got to do the torques again. So I got mass of the block, gravity, length, plus mass of the rod, G, L over 2, equals 2. Go ahead and plug in. Mass of the block is 0.5 times 9.8. Length of the rod is 0.6. Plus mass of the rod is 2 times 9.3. I got 0.3 by dividing 0.6 in half. Equals 0.42 alpha. You get 21 radians per second squared. All right. That was pretty easy. That was actually pretty straightforward. Just understanding torque, how that works. So let's move to question 2. It says Guadalupe has a motorized globe on her desk that has a 0.16 meter radius. She turns on the 4.25 watt motor and the globe begins to spin. The globe starts from rest and has a final rotational speed of 0.628 radians per second. The globe reaches this speed in 25 seconds. A. So this is it's okay. What is the angular displacement during the 25-second time interval in radians? All right, so angular displacement is delta theta. That's what we're looking for. So let's list out what we know. It gives me in 25 seconds. So I got time is 25 seconds. It has initial velocity is 0. It starts from rest. And it has final velocity is 0.628 radians. So knowing all this, I got all this. I got 4 of them. It's pretty straightforward. I look at my constant angular acceleration equations, and I'm going to use this one. Delta theta is 1/2 initial final times time. Plug in. So solve for what you need. 1/2 initial 0 goes away. 0.628 time is 25. Bang, bang, bang. With a new calculator, you should get, what do I get? 7.85. So it actually goes through in that 25. The globe spins around 7.85 radians. That one's super easy. All right. B. What is the linear speed of a point on the globe's equator? So we're going to be at the radius since we're at the equator. Again, we got the final velocity here is 0.628 radians per second. I got radius since we're at the equator, 0.16 meters. Wow, we want to know velocity, right? Yeah, easy. Plug it in here. We get 0.10 meters. Pretty easy stuff so far. All right, let's see what he said. What is the average torque provided by the motor during 25-second time interval? So what we need here is we know that the power is equal to 4.25 watts. We know it turns through a distance of 7.85 radians, and it has a time of 25 seconds, right? So I want you to remember definition of power. Power is work over time. Our linear work is force times distance divided by time. So that's work, and that's time. So if I rewrite this for rotational, force is going to equal torque. Distance is equal to beta. Time is still time. Okay? So that's the equation we're going to use here. I think we got enough. P, yep, T, yep, beta, yep. We need to find torque, right? So my power is 4.25. Torque is what I'm looking for. Theta is 7.85. And time is 25 seconds. So if I calculate the torque, I'm going to get 13.5 meters. That's it. See, right? Done. 2. Yep. All right. Question 3. Okay. So this one is going to be a little bit different than what we did in the basic Atwood machines where we had a massless pulley. This one has mass, so it's going to be a little bit different than our calculations from Newton's laws chapter. So let's look at A. What's it say? I'll read the question. In the diagram below, two bodies of different masses, M1 and M2, where M2 equals 2 times M1, are connected by a string which passes over a pulley of no friction but has rotational inertia equivalent to a solid disk where I equals 1/2 mr squared. The pulley has a mass of half of mass 1 and a radius r. On the diagram below, draw and label vectors to represent all the forces acting on M1 and M2. All right, one's easy, straightforward, right? So let's go ahead and bang this out. 1, there's tension pulling up, we'll call it tension 1, and there's weight going down. So I got weight 1 equals mass 1 G. Super easy, super straightforward. So let's look at 2, right? Mass 2. You're going to have T2, weight 2 equals 2m1 G. All right, I wrote it as 2m1 because you want to keep it, so I know that m1 is, it's going to be easier. I'm not going to have as many variables. I know I can write it as 2m1 because it says that the mass of 2 is equal to twice it. All right, so that's easy. That should be straightforward. You got 2 different forces acting on each of the masses. All right, easy question number 1, or part A of this. All right, so let's go to See what B says. All right, so B says, qualitatively describe the forces acting on M1 and M2 and indicate why they cause the pulley to rotate. All right, so we just talked about, there's two forces acting on both M1 and M2. Pretty easy, right? Mass of each of them pulling down and the tension's pulling up. All right, the key to this is because of the moment of inertia of the pulley, the tensions are not going to equal. Okay, so therefore, T2 is going to be greater than T1, and that's what causes the disc to rotate. The greater T2 force gives the torque to the, what's called, the pulley. So, I don't know what to write there. So hopefully you just listen to it. Nothing to write. So two forces on each. T1 is not equal to T2 because of inertia. And because net torque cannot be 0 because there is a acceleration. So I guess that's it. All right, cool. See. Describe how you could determine the magnitude of the acceleration of the system in given quantities and fundamental constants. All right, be sure to explicitly describe the calculations you make. All right. But do not actually do any algebra or arithmetic. Oh, well, I did algebra and arithmetic. So what we can do first, and I'll walk you through the calculation, is let's write force equations for both masses. So I got mass 1, mass 2. Pretty straightforward. Let's set that the direction that they're going to move. So T2 is going to be moving down, or I mean, mass 2 is going to be moving down, mass 1 is going to be moving up. So down is going to be positive for 2, and up is going to be positive for 1. So that gives me, if I do summation of the forces in the y equals ma, I got T1 is going up, we said that's positive, minus M1G is pulling it down, equals M1A, because it is accelerating. Mass 2, let's do the same thing. Summation of the forces equals MA. In this case, we said down is going to be positive, so I got 2M1G, that's the weight, minus T2 equals 2M1A. So these are important. Those are our force equations right there. Okay, so we're gonna hold that. So we're looking at the forces here. Obviously, force has to do with torque. So now let's look at the torque acting on the pulley. So summation of the torque equals I alpha. All right, so let's think about what we got here. T2 is what? Pulling down, so that's counterclockwise. So let's put that as positive. So the tension, which is equal to the force times the radius of the circle, gives me the torque. Minus T1 is pulling it pushing it this way, all right? Going that way around the circle, so it's going to be opposite direction. So I got T1 times the radius of the circle equals I alpha. All right? So now what we need to do is we're going to kind of work and get acceleration here. So we're going to get acceleration here. Now, if you remember, this is an equation you got to kind of remember here. Angular acceleration is equal to tangential acceleration divided by the radius. Tangential acceleration, in this case, remember it's tangent to the circle, is the same acceleration as we're talking about here and here. So I get AR. Okay, so I'm going to plug that in there and rewrite. And I know I, right? It gives me I. It gives me I. Yes, it gives me I. I equals half MR squared. Okay, so let's plug in here. Man, I'm running out of room. All right, so I'm going to plug into this equation over here. I got T2R minus T1R equals, I is this, right? It's 1/2 mass of the pulley times radius of the pulley squared. That's I. Alpha becomes this, A, R. R is going to cancel out the squared. So let me see. Yeah, let me rewrite that. So I get T2R minus T1R equals 1/2 mass of the pulley R A. Like terms right here, right? Like terms. So basically, I'm going to pull it out. I'm going to skip a step here. I'm pulling this out, and I'm going to get T2 minus T1. There's going to be R out here, but that's going to cancel out this R here. So I get 1/2 mass of the pulley acceleration. All right. So let's kind of stop there for a second. This is key. This is my Newton's second law for rotational motion here, right? So this is what we got. We got it from that. Now I know I have equations right here of T1 and T2, T1 and T2 in it. So what I'm going to do is I'm going to solve. So I got to make sure I write this down because I need to copy this onto a clean sheet. So we got room to work here. G equals M1A and 2M1G minus T2 equals 2M1A. And then our rotational is T2 minus T1 equals 1/2 MPA. Mass of 48. All right, so let's clear this. Still C. All right. So what I'm going to do is I'm going to solve those equations and get an equation that says T1 equals and T2 equals. Okay, so my equation, if I would solve the one for T1, I would get T1 equals M1A plus M1G. So that's what T1 equals. So I'm going to solve that other equation for T2. So I get T2 equals 2M1G minus 2M1A. So those are those two equations that I had on the last screen, but instead I just solved them for tension 1, tension 2. Well, know what I got? I had that equation, the rotational torque equation. I'm going to plug those in. So what I get is I get T2, right? So I get 2M1G minus 2M1A. Subtract T1, that was from that equation. So I get minus M1A minus M1G, because you distribute the negative in, equals, the right side of that equation was equal to 1/2 mass of the pulley times A. And actually, let me change this. Remember the mass of the pulley? What was the mass of the pulley? It was 1/2 of M1. So let me erase this and actually type in the mass of the pulley as 1/2 M1. So that's mass of the pulley, but I plugged it in for what it told me it was. So in fact, if I redo this, I would get 1/4 1/4 M1? Yeah. Let me erase this. 1/2 times 1/2 is 1/4 times M1. So that's basically the mass of the pulley just solved in for everything here. So now all you have to do here is you're going to solve for A. Is there M1 in every term? Yeah, M1 cancels out. Bang, 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 bang. So I get 2G subtracted by 1G. So I get G. Right, that cancels out. That cancels out. I get G. Negative 2A minus, I get minus 3A equals 1/4 A. Right? Yeah, that's right. So let's get A's to this side. So I'm going to add 3A. I get G equals, I got to do this. What is it? 12/4. 13/4 A. Not 14ths. What the heck? Yeah, then what do I do? Get rid of it. So I get A equals. So I multiply by the reciprocal, which is 4/13 linear acceleration. That was pretty tough. That was pretty tough. But you just got to remember, you're going to use Newton's law, Newton's second law for linear motion. Get the forces acting on it, because the force causes the torque. Then you're going to relate it to Newton's second law for rotational motion. The torque causes the rotational acceleration. Was that C? Yeah, we done with number 3? Yeah, we're on to question 4. So we got a little drawing here. What's A say? Yes, I'll draw it so that way we can talk through it a little bit. All right, so we got a ramp with a loop-to-loop with a radius of 2 meters. We got a ball, mass 5, and has a radius of 0.125. And we know at the top of the loop it has a velocity of 5.45 meters per second. So A asks, or let me read. A solid sphere begins at rest, rolls down the incline, and through a 2-meter radius loop without slipping. The sphere has a mass of 5 kilograms and a radius of 0.125 meters. When it is at the top of the loop, the ball has a linear speed of 5.45 meters per second. Indicate what variables determine, so A, indicate what variables determine the sphere completes one trip around the loop with this specific speed at the top of the loop, and justify your answers qualitatively without using a equation. So what this is going to be talking about is this is going to be a conservation of energy problem here. So we know we're going to set the energy because it says the sphere begins at rest. So if we're looking at the top, right, excuse me. If the sphere begins from rest, then we know that kinetic energy at that point equals 0. It's not rotating, so that's translational. Kinetic energy rotating at that point equals 0. It has a height, so therefore it has gravitational potential energy, which is equal to mgh, right? Mgh, very easy. So what needs to happen is, when we look at it, we know that the energy total initial must equal the energy total final. So if you look at the loop at the highest point here, we know it's going to be moving. Here's this velocity. It's going to have translational energy. It's going to be rotating because it's rolling. It's going to have rotational. it's actually going to have potential energy still because it's at some height above the ground. Okay, so what we're going to be doing is looking at, are these energies total, and we can figure out if the ball is going to get through it, looking at the height, see if it has enough total energy of the energy required at this point here. So you're going to use this factor, knowing that these are the energies at that point. All right, so that was A. B. Says, justify your answer about what variables determine the sphere completes one trip around the loop with a specific speed at the top of the loop with appropriate equations. So justify your answer about what variable determines if the sphere. Oh, so we need to know a height. So the height is what determines it because it sets the initial thing here. So what we're going to do for B is we're going to find the height, right? So let me clear this because that's what sets it. So the mass is set, gravity is set. The only thing we can change is the height, all right, where we put it on the ramp. So let's go ahead and look at that. So B. So I'm going to start with this. E total initial has to equal E total final. And this is in the loop, and this is at the top. Okay, so that's in the loop, that's at the top. So like we said, we got MGH here. So MGH, that's it, right? We had no other energies here. So let's go ahead and plug in here. I got translational kinetic energy, which is equal to 1/2 mv squared. Plus, I got rotational kinetic energy, which is equal to 1/2 I omega squared. And we got potential energy, which is equal to mg. Now, we don't have the height of the loop, but we have to take into account the radius of the ball. So at the top of the loop, let me draw the loop over here, right? The ball is right here. We know the radius is, well, we know R, okay? So we want the height of the center of mass. So watch what I do here. If I do 1R, 2R, doesn't that give me the height? So that's R and that's R. That gives me 2R. That gives me the height of the loop. But I don't want the total height because it's the center of mass is at the ball center, and it gives us the radius of the ball. So the actual height is going to be this right here, 2 times the radius, so 2 times our height, minus the radius of the little sphere, puts us at the center of that sphere. In other words, the center of mass of that sphere, and that's how we're going to calculate potential energy. So I'm going to put that, and instead of H, I'm going to put it in terms I can work with, 2R minus little r, that's the radius of the sphere. So what I can do here, I know I, they give me I, yeah, they give me I. I equals 2/5 mr squared. I know velocity, I know V, I don't know angular velocity, but I can get angular velocity out of it. So let's start simplifying this to get it in terms that we can use. mgh equals, I know all those terms, so 1/2 mv squared plus 1/2 I is equal to 2/5 m r, well, that's capital R, sorry, squared. Omega squared, all right, is going to be v squared over r squared. And we just do this. All right, so let's see what we can cancel out here. So let's start in this middle here. R squares cancel out. What I got? 1/2 times 2/5, that's be 1/5. So I got mgh equals 1/2 mv squared plus 1/5 mv squared plus mg 2r minus little r. Well, everyone has an m. Cancel those guys out. I get gh 1/2 v squared plus g 2r minus r. I can plug in. I got all these numbers here. 9.8 h equals 1/2 V, what was that, 5.45? Squared plus, yeah, I mean, you could have combined those. That was kind of stupid. Squared plus 9.8 times 2R. So that's 4. 2 times R is 4. I don't do that. 4 minus, what was it? It's 0.125. When you solve that all out in your calculator, you get a height of 6 meters. So that is the minimum. That's the, well, I'm sorry, not the minimum. That, because it gives us the velocity. It tells us the ball is going this fast around the loop. So that is the height that the ball needs to be placed so that it is traveling at 5.45 meters per second around that loop. And that finishes up your free response questions. Hope that helped out.